Hello everybody and welcome. We are the TCNJ UAV team from the College of New Jersey. This is our technical design and flight readiness review video. Our advisors are Dr. Alabsi and Professor Sepapor. My name is Anthony Russo. I am the team leader and I am in charge of UAV tuning and controls.
My name is Thomas Egan. I am responsible for the drop mechanism.
My name is Thomas Ramu. I'm responsible for the camera and gimbal.
And I am Steve Madraza, and I am responsible for the UAV design and stability. Going over the design requirements, we have to carry 5 water bottles for the full 10-mile waypoint course to achieve maximum scoring, be able to maintain a top speed of 30 miles per hour for 30 minutes to leave time for airdrop, safely and accurately deliver each bottle while hovering at an altitude of 100 feet, use remote control and gimbal to search the drop zone for ODLC targets, have a multi-mile communication link to ensure connection during entire flight. Just going over a brief design review, we have a vertical takeoff or landing multi-rotor vehicle that is a pinwheel configuration with an X8 design, featuring a motor-to-motor distance of 5 feet. Our overall configuration is 30 pounds without any payload.
For our imaging, we decided to go with the Canon PowerShot SX70 due to its 65 times optical zoom. This is placed on a 2-axis gimbal for roll and pitch, which incorporates remote zoom using 2 push rods and an onboard microservo. The camera streams through the HERE link to the laptop and has manual ODLC from RC inputs. Some alternatives we considered were the Sony a6000 and Canon M50 Mark II cameras. However, these required exterior lenses, which added unneeded weight, as well as a 3-axis gimbal, which also added unnecessary weight and power consumption.
Our airdrop mechanism was designed to safely deliver water bottles from 100 feet above ground level. It utilizes high friction spools to slow the descent of each bottle using magnets to increase the friction. A single servo motor is used to release all 5 bottles individually at their own waypoints. The string stays attached to the bottle and is released from the UAV and later removed by the judges on the ground. We decided to use magnets to control the speed of descent instead of motors to reduce the weight and power consumption on the aircraft. Parachutes were also considered as a lightweight design, but were determined to be too inaccurate to be competition ready.
In order to communicate between the UAV and ground station, our team has decided to utilize the HereLink remote and air unit to transmit RC data, telemetry, and video. This system has a transmission distance of up to 12.5 miles, utilizing the 2.4 GHz frequency. Alternatives that we considered are Express LRS for RC data, the RFD 900X for telemetry, and the Ubiquiti long-range Wi-Fi for video. In order to communicate between our drop mechanism, zoom mechanism, and gimbal, we've decided to use the Radiomaster TX16S communicating to an FR Sky receiver. This has a transmission distance of up to 2,000 feet.
In order to make the aircraft design as lightweight as possible as well as rigid, we went with square carbon fiber tubes for the arms, round carbon fiber tubes for the landing gear, lightweight carbon fiber sheets for the top and bottom structural plates as well as the motor mounts, and the component mounting plate is made out of cast acrylic as it is non-conductive.
In terms of the aircraft component selection, we decided to use the Cube Pilot Cube Orange Plus for the flight controller, the Hex HERE 3 Plus and HERE Plus base for the GPS and RTK. As for the propulsion system, we decided to use 8 Taro 6012 132 kV motors pushing 8 24-inch propellers. Driving this combination are 8 high-voltage 80-amp ESCs running BL Heli 32. This accounts for 160 pounds of thrust total.
Here we have a diagram showcasing the ESCs, the arms, the motor and propeller pairs, and the component mounting plate. This diagram showcases the motor mounts, the 2 structural plates, and the landing gear.
This is our component mounting plate. Here we have the GPS, flight controller, and flight controller BEC, as well as the receiver for the telemetry and RC data. We also have the power distribution boards for both the top 4 and bottom 4 motors.
Before deciding on the X8 configuration, we had alternative frame designs in mind, such as the hexcopter. However, it does not provide enough lift to support the drop mechanism and gimbal, and the octocopter, which thrust to weight ratio is not comparable to that of the X8 design.
In order to autonomously control the aircraft, we utilize Mission Planner ground control software. This allows for input of GPS coordinates as well as utilizing the fly to here mouse clicking option. Waypoint accuracy radius is set to 25 feet to allow for smoother transitions between coordinates. Altitude at each waypoint is also configurable from the ground station. In terms of our ground station, The HereLink will be tethered to the laptop running Mission Planner. A portable power supply is used to ensure the laptop stays fully charged, and the safety pilot will maintain consistent eye contact with the aircraft while holding the HereLink remote. Throughout all of our aircraft testing, safety was always our number one priority. We prioritized life and property over the aircraft. No flights were conducted over or near pedestrians or wildlife, and all tests were conducted on fields away from major roadways or property. During testing, we made sure to follow all FAA rules and regulations. We never exceeded 400 feet of altitude. We flew within a constant line of sight of the aircraft. All operators had attained trust licensure. The vehicle was registered to FAA Drone Zone, and when applicable, we have received LANC approval for flying in controlled airspace. In terms of battery failure, our circuit configuration allowed the drone to land safely in case a series pack fails during flight.
For our ODLC performance, the bottom right video proves that the quality is maintained at zooming in at the 65 times optical zoom at around 125 feet. The top left video shows that the gimbal was PID tuned for stabilization through the Basecam graphical user interface. The bottom left video shows how the RC inputs from the RC receiver control the gimbal through the Radiomaster TX16S controller.
For our airdrop testing, the left video shows that the servo motor is able to release all 5 water bottles in order. The right video shows our spool testing, in which initial spool testing was done from a height of 50 feet. Multiple iterations of the spool were tested with different numbers of magnets and magnet radii. The bottle is allowed to freefall before being slowed by the magnets, and the freefall distance was tuned to achieve optimal descent time as well as impact speed.
In terms of communications performance, the farthest distance between the aircraft and GCS has been 1,100 feet. During this testing, we have experienced 0% packet loss. In all of our testing, we've only had one communication dropout. This was a loss of RC input due to carbon fiber interference. It was solved by changing the antenna location on the aircraft to allow for minimum interference. During this event, we successfully completed an autonomous RTL and landed safely.
Our aircraft testing was comprised of 13 total flights. These added up to a total of 71 flight minutes. During our testing, we achieved a top speed of 40 miles an hour and estimated a 15.4 mile range based off a 5-mile autonomous flight using only 32.5% of our battery capacity.
Of our 13 total flights, 4 of them were autonomous. 49 waypoints were successfully flown with 100% accuracy. During these flights, an average error of 25 feet was used to allow for smoother arcs between the waypoints. 2 minutes of manual flight were used per autonomous flight to allow for manual takeoff and landing.
This safety video demonstrates the safety pilot's ability to take off, fly 1,000 feet away from the safety pilot, and then manually land the aircraft. Here the aircraft is seen reaching 1,000 feet away from the safety pilot. Here the pilot is seen successfully landing the aircraft. This safety video shows an autonomous flight over 200 feet away and manual takeover and landing of the aircraft. The autonomous flight is started using a fly-to-here command. The aircraft is manually taken over by the safety pilot almost 500 feet away from the GCS. The safety pilot successfully lands the aircraft. This video shows the team's attempt at a 12-mile range test. As seen in the video, the aircraft experiences a vibration error. After this error, the safety pilot takes manual control of the aircraft and brings it to land. Prior to this error, autonomously the vehicle was able to travel 5 miles. The safety pilot was able to safely land the aircraft. After believing to have solved the vibration issue, the team attempted another 12-mile test flight. Unfortunately, during this flight, another vibration error occurred. This led to propellers fracturing and detaching from the aircraft during the flight. More research is being done to prevent future incidents like this.
Over the past year, our team was able to construct an X-8 octocopter which was successful in a 5-mile autonomous flight using 32.5% of battery life. This gives us an estimated 15.4-mile range without any payload. During the testing, we were able to reach a maximum speed of 40 miles per hour and complete successful autonomous return to home landing. This concludes our technical design and flight readiness review. Thank you for watching.